Hi there, and welcome back to this channel. In this video, we are going to talk about vector torque and dipole moment. And one of my major goals in this video is to not just show you what happens to a dipole in an electric field, okay? That is the effect of the electric field on a dipole, but also to be able to clear your misconception about the value of the potential energy that a dipole has in an electric field, when it is maximum and when it is minimum. Students usually find it confusing, okay? So I'm going to demystify it for you in this video. Just make sure you listen to the end and follow me as I go chronologically. All right, let's go. So now, what is the vector torque? What is dipole moment? You already know that dipole moment is the measure of how evenly dispersed in a system the charges are, right? Okay, so the dipole is, okay, the dipole, how evenly distributed electric dipole is. That's what dipole moment, okay? Or the mathematically we say is the product of the charge of a particular charge and the distance away from the other charge, of one charge away, and the product of one charge and the distance away from the other charge. You understand? Okay? All right. So, but first, let's analyze a field, an electric dipole in an electric field. Okay? So let's say I have an electric field that is going in this direction from the bottom of my board to the top. Okay? And I have my charge 1. Let's call this positive charge Q1, and my Q2 around here, let it be the negative charge. Now the dipole moment is going to be between them, right? My dipole moment, right? So my dipole moment P here is going to be what? Q2 times this distance of separation. So let's call this distance of separation, let's call it D. Does that make sense? So it means that midway between it will be my axis, right? The midpoint of the axis of the dipole, okay? So now, if this is my electric field going everywhere on the board or going upwards everywhere on this my board. Now, what will happen to this guy? Now, the force that this guy is going to feel. Now, let's first analyze the force. The force that will be on my first charge, let's say F1, okay? Or let's call it F positive. The force on my positive charge Q is going to be upward, right? And it's going to be given in this my analysis here, it's going to be upward, that is in along the direction of my E, okay? That's for my positive charge. It's going to move in the direction of my E. Now, and that force in value, remember the formula F equal to EQ. Do you remember? Okay. So if you remember this from that value, that is the electric field times what? Times Q, times the value of the charge. That's what the F1 is going to be. EQ1, okay? So this is going to be the value of my electric field, the value of the force on the charge 1, okay? And it's going to be positive, okay? Now, positive because it's moving in the direction of my electric field. So I call the direction of my electric field the positive. So F1 is acting along EQ electric field. And F2, which will be the force on, let's call it F minus, okay? Is going to be the force on my negative charge Q2, and that will be what? Also be given by what? EQ2. Does that make sense? Okay? But notice this one is going to be what? Negative. So the sum of forces on this my dipole, this one is going to be acting in the opposite direction. That is provided this one is acting in the upward direction, this one will be acting in the downward direction. I hope that makes sense. Now, this is the case. If this guy acts in upward direction for another electric field, this one will act in the opposite direction, downward. Why? Because this is positive, this is negative. So in the dipole, if the force acts in the forward direction for one, it will act in the backward direction for the other. Because the dipole, they have different charges, they are opposite charges. Okay? So my F net, or sum of forces, is going to be what? F1 plus what? F2. Remember, F2 is negative, so it's going to be F1 minus F2. And being equal, since this guy, Q1 and Q2, since Q1 and Q2 are equal but opposite, in a uniform electric field, keep in mind that my electric field is uniform, because in a non-uniform electric field, this will not be the case. So in a uniform electric field, since Q1 and Q2 are equal, then F1 and F2 are also equal, which means that F net is equal to what? 0. So the sum of forces that are acting on the electric dipole is going to be what? 0. Okay? But here's the case. Now you can see that if this was my my dipole, there's a force acting upward and there's a force acting downward. What is this? The force F net may be 0, but it creates a couple, right? Both of them, F1 and F2, they form a couple, right? Husband and wife. Okay? Because they are acting in opposite direction. Remember, when you have two forces acting in opposite direction that are non-collinear, they form a couple. And because they form a couple, then what will happen? There is torque. There is torque. Okay? There is torque in this system. Okay? The force of rotation, right? The force due to rotation. That causes rotation, rather. So what will now happen? Now, my torque here, remember that torque is going to be what? The force acting on the body times or multiplied by the radial motion. Okay, which I'll represent with R in this case. That is the rotational distance, the distance of rotation that the body rotated by. Okay, I'm still going to come to this diagram. Okay, so but my torque in this case, which represented by tau, is going to be equal to my vector R because it's directional. This one is going to be in this direction, this one is going to be in this direction now. Then multiplied by my F. Now, what kind of product will this be? Because our torque is a vector, it's going to be the cross product of R and what? And our force. Okay? Now, this is our torque. This is our torque. But there's something about this torque also. Because this guy is not exactly on the x-axis, so we cannot have it this way. Our guy is at a particular angle in our uniform electric field. Our dipole is at a particular angle in our uniform electric field. So it will not be as sweet as that. What will happen is that you will notice that there's a distance here between our axis of the dipole, and the electric field. So this angle here, let's call it theta. So by the time we resolve this here, we're going to be opening the angle. Or when you want to take vector product, you say that it's what? Or cross product, it will be cross product of this sine of theta. I have released a video on what this is before. Do you understand? So cross product is going to be what? R times F sine theta. Okay? And that's because we have placed our dipole at a particular angle relative to the what? Electric field in which the dipole is. Does that make sense to you? So this will be the value of our dipole, of our torque. Okay? But remember also that our F we gave to the what? EQ here, right? So that's going to be what? E sub Q. Recall this, right? Now, if this is the case, then we can say that our torque is going to be equal to what? R cross E Q. Okay, now our R here, we can use D to represent it, which is distance, right? So we can say it's distance, that will be D. Okay, then sine theta. I hope this makes sense to you. Now, if this is the case, then recall also that our dipole, electric dipole, is going to be what? Q times distance. Does that make sense? So if that be the case, then dipole moment, not dipole moment. Our dipole moment is Q times D. So we can say that Q times D is already dipole moment, so that our torque becomes PE. Does this make sense? Okay? Dipole moment is vector. Electric field intensity is also what? Vector. So we can say that our torque is this sine theta, or PE. If the angle our torque, our maximum rotation due to the torque will be observed when angle between them is what? Is perpendicular. That is when our dipole is exactly perpendicular to the electric field. So that is when this guy is like this and our electric field is pointing everywhere up or down. Does that make sense? So if this is the case, then our value torque is going to be what? P dot E vector. You understand? So that's going to be the value P cross. Okay? All right? So this is going to be the value of our torque. Now, what can we make out of this guy? What can we make out of this guy? So this is going to be the value of the torque. I said I wanted to explain the potential energy. Now, since this guy, our dipole, exists in a uniform electric field, then it's going to have potential energy. Why? Because it's going to, the torque will cause it to, rotate. Okay? So when the torque causes it to rotate, by the time the torque causes it to rotate, there's going to be an energy in the system, right? Because work is being done here, work of rotation, right? So if that's the case, then the work done on the system is given by negative P dot E. Now, what students don't understand is the fact that, remember that my torque is P cross E, that's intentional, okay? And my potential energy PE is what? P dot E, because because potential energy is scalar, okay? Even though I can represent this in my scalar form, I can represent torque in scalar form. That will be torque tau equals QED, in case you have seen that in your sin theta, in case you have seen that in your textbook before. But keep in mind that this one is potential energy, where U is what? Potential energy. Now, our U is negative PE. Why? So this is what usually confuses students. It is because if you place our dipole, let's say our dipole exists on this marker. If you place it here, the moment it stays here, the field does work of rotating our dipole in such a direction that will cause it to align with the electric field. Does that make sense? First, note that is a vector product, dot product, scalar product. So it means that I can still say that U is equal to what? Minus P dot E cos theta. Do you remember? Cos theta for dot product. Okay? I want you to understand this. It's the negative I'm trying to explain first. Okay? Now, before I even explain the negative, okay, let me explain the negative. The negative because whenever the system does work, whenever the field does work on our whatever is there, whatever is in the field. In this case, our dipole is in the field. Because the field is doing work on the dipole, the energy of the dipole will what? Reduce. But the field is doing what? Positive work on the system. Okay, look at this now. If I throw this body up, when this body is going up, G will be what? Negative. Does that make sense? So because G is negative, the weight of the body is also what? Negative. Does that make sense? At the moment of going up, right? But by the time it's coming down, the field is now doing work on the body that is coming down. But when it was going up, it's negative because when it was going up, this guy is doing work against the field. Does that make sense? So, because our torque has to rotate this field, this dipole, such that it aligns with the electric field, then we say that it is what? Negative. Why is it negative? It is decreasing. The potential energy of the system is decreasing because the field is doing work on the system. Let me reverse it. What if by ourselves, we now have to rotate the body against the field? If you rotate the body, it means that the dipole is now doing work against the field. Does that make sense? Does that make sense? So because of that, the potential energy of the dipole will be increasing. Do you understand now? Because you are doing work against. I've explained potential energy before. If it takes me, for example, if I have a positive charge here, and I want to take a positive charge Q, I want to take it towards here, then I am doing work against the field of this guy, right? I'm doing work against the field of this guy. So I'll be what? Negative. Does that make sense? So I'm doing like negative work. Does that make sense? But if this guy is leaving the field, he's doing work for this, relative to this guy, relative to this our positive charge here, because it's moving in direction of this positive charge, the potential energy of this guy will be increasing. P of this guy will be what? Increasing. But it's doing negative work against what? This guy. Does that make sense? Okay, it's moving towards the guy, so it's doing work against the guy. But if you see this guy, but if this guy were to be moving away, because this guy is positive and positive, and they have to repel each other, this guy is doing work. The field is doing work on the body. Does that make sense? It means that the potential of this guy, potential energy of this guy, what will reduce. So the value of the potential energy of this guy will become negative PE. But in this case, it will increase, it will become positive PE. Does that make sense now? I hope you understand. Potential energy of this guy will be increasing because it's going towards the field, towards the positive charge, and the field of the positive charge is saying, go away, go away. But this guy, the field of this guy, if this guy were going away, then it means that it's the field that is doing work on this guy because it's saying go away, and it's also actually what's going away. So because of that, the potential energy of this guy will reduce. But because this guy is doing work in this direction, then the potential energy of this guy was increasing. So the same way, when we naturally place a dipole in our field, the torque tries to rotate it. And so because the torque is the torque of the field is trying to rotate it, it's the field that is doing work on the dipole. So because of that, first, why is it rotating it? To align it. Okay? The moment it aligns it, the angle between the field and the dipole becomes 0. And when you have 0 here, then this U, electric field, what? 0. And why will it be 0? So this 0 will be the minimum value that the electric field can have. Why? Because cos 0 is cos 0 sine 0 is 0. So cos 0 will be 1. Okay? Okay, cos 0 is 1. I'm trying to bring up something. Now, if the torque rotates the electric field, it's not hard, just listen. If the torque rotates the dipole rider in the electric field, then it aligns it so that the angle between them will what? 0. And cos 0 will be 1, I think. Yes. So it means that at that time, the body will have minimum energy. Yes. So cos 0 is 1. So U will be what? U minimum. Okay? Which will be equal to what? Minus PE. Minus PE. That's what the electric field naturally wants to do on the dipole. It wants to rotate the dipole such that it gets to align with the field, and the angle between the field and the dipole is 0, so that our distance will be minimum. Our potential energy of the system will be what? Minimum. So that will be negative PE. Now, when is it maximum? It is maximum when you rotate this guy in anti-parallel direction. You know these two lines are parallel. Why these two lines are anti-parallel? Why? Because although they are parallel, but they are facing different directions, so we call them anti-parallel. So the angle between them will be 180 degrees. Once the angle between them is 180 degrees here, cos 180 degrees is minus 1. So if it's minus 1, minus cancels minus, and U will be maximum. So that what? P dot E. Does that make sense now? So you see this one is negative, and this one is what? Positive. So this will be the maximum potential energy at the point where the dipole is what? Anti-parallel. Anti-parallel to the field. Does that make sense? But it's minimum whenever the dipole is parallel, not anti-parallel, parallel to the field. Okay? And that is the work of the torque. The torque wants to reduce the potential energy of the system by rotating the dipole such that it aligns with the field. Right. So that is what all of this is about. And so those are the formulas you need for calculation. But just so that you understand intuitively why the electric dipole rotates, why the electric dipole, the torque rotates the electric dipole. So this will be it for this video. Do well to subscribe and turn on the notification bell. Please subscribe and share the video. God bless you.